right, so a little disappointed with how little people are here. I think these reviews are really helpful in doing well in the final. But kind of go through these. So mentioned a couple things off the top. I put up both the recorded lecture from this section, but also my previous one last class. I'm working through practice exam A with them. I'm working through practice exam B with you. So you kind of should have a little bit different problems to work through. I'll put up the same thing today. You kind of have both sections so that you've got some additional problems, or you can see me work through them if you run into any problems in those practice exams. The last day to kind of turn in those two last to Excel and that Connect is the end of the day today. So over the weekend, hopefully, maybe not until Monday, I will get kind of the grades posted up there and try to hopefully have some time to grade quite a few of them on Wednesday, where I can drop the lowest Excel and drop your lowest Connect and get those scores up on Canvas, right? Just like I got the iClicker scores kind of with your 3 lowest drop up there in Canvas. So you would have an idea about where you're at in every category except for the final. So you could put in, and we'll ignore this. This was work. Oops. You could put in your Excel grade with the lowest drop. Once that's up there on Canvas, you got your iClicker grade with the lowest drop, Connect, your first 2 exam scores. You could then play around with, well, how bad could I do and still end up with a B in this class? Looks like I could do really, really bad. And so maybe, you know, if I've got other classes where I'm kind of on the precipice of a different grade, maybe I put a little more time into that class. Or, you know, if I know that I really want to get an A in this class, and if I want to do that, I've got to get, you know, really, really good score in this final. Well, then maybe I put a little more effort in, right? So we kind of just really let you know kind of where you're standing going into that final next week. Okay. Yeah, so generally so this is outlined in the syllabus, but basically at the end of the semester, what I'll do is I curve everybody's grade by a half a point, which essentially rounds up, right? So like if you were above a 90, like 89.65 would get rounded to a 90. I also kind of outline what the grades are. So it's like 60 to 62 would be a D minus, 63 to 66 is a D, 67, 68, 69 would be a D plus. Yeah, so I kind of do a half point curve and then round it. So you just see kind of your integer kind of grade there. But yeah. Any other questions? So logistics wise in the exam, I'll bring the T tables in the form of the sheet. Right, about 2 hours. I believe this one is Thursday at 9:45, but let's make sure that my memory is correct. And I'll probably put up a kind of reminder on Canvas next week. So if we go down, yep, Thursday 9:45, right? So usually got an hour for 20 questions, 2 hours, you got 30, so time really shouldn't be an issue. I kind of mentioned last class, half of it's going to be linear regression stuff, half of it's going to be this 2 population, kind of comparing sample means, comparing sample proportions, which is a lot more of what we'll focus on today, right? We did a lot of regression stuff earlier this week, and on Wednesday, I'll kind of focus a little bit more on those 2 population questions today, right? Unless any, you know, people have questions about linear regression they want me to kind of start out with. Let me see if there's anything else that I wanted to mention off the top. So we've got mentioned updating the grades. Oh, after tonight's due date tomorrow, I will get posted up the answer keys to both those Excel assignments. So that way, you know, that 5th Excel, for those of you that did it, is very like not a lot of Excel and a lot of interpretation, right? And so it's a really good one to like know how to do, like, how could I work all these out by hand? Like that portion of Excel is really going to be a good study tool, right? So I'll get that answer key up quickly so you can kind of go back and look at that as well. Okay. Any questions from me before we kind of dive into more like review? Logistic questions about the exam. Okay. So I'm sorry that it's on a Thursday, but at least it's not a Friday. I've had those before. So let's go to practice exam B. All right. And kind of start on problem 2. So I kind of outlined last class the different types of problems we could have and what types of distributions we use, right? So anytime we've got proportions or sample means where we know the population variance, those are going to be scenarios where we use that standard normal or the Z tables. Anytime we've got sample means but sample variances or matched pairs examples, we get to use that student T, or we have to use that student T. Now here I gave you an example where we kind of have only sample variances, right? S squared for both groups, right? That kind of indicating it's sample. We'll work through this one. You know, a lot of the difference in sample means, the only difference when we have population versus sample variances, the structure of all the equations look the same. The only difference is we use the student t distribution instead of the standard normal. So a lot of this stuff that we'll work through these would apply to a problem where you were given a population standard deviation or population variance. It's just that you'd be using the standard normal to look up z values as opposed to looking up t values. So here I've got kind of this BMI example where I'm looking at Indiana and Ohio. I've got my sample variances. I've got sample sizes from both groups that are given to me. And I'm saying, okay, assume you want to find a 95% confidence interval. Okay? So you want to find a 95% confidence interval for this difference between Indiana and Ohio's BMI. And I give you this assumed true degrees of freedom of 50. So remember, when we have, if we look at our formula sheet, and once again, I try to put everything in order, so it's not trying to trick you or anything like that. Like kind of the exam and the formula sheet flow with how we cover things in class. So here's our sample means when we only have sample variance confidence interval equation. Now, usually when this is the case, we have to find the degrees of freedom with this crazy equation. I said, I'm not going to make you do that. I'll always give you that degrees of freedom. So here I told you it was 50, right? But from there, it's really just a matter of plugging things in. So I think I had 29 was Indiana's BMI. Sorry, 28 was Indiana's, 29 was Ohio's. I then have kind of my sample variances I was given. Can't remember what they are, so I'm going to have to go back here for a second. So we've got what? 9 over the sample size of 40 for the first group, which was Indiana, and then 16 over 50 was the variance over the sample size for my second group. So all I was doing there, plugging everything I knew into this equation, I end up with something like this. Okay? Just plug my values in at this point. The next thing I need to do was, well, what t value gives me alpha over 2 on each side? Right? I believe I had this was the 95% confidence level. So what would my alpha value be? Yeah, 0.05. So it's very similar when we find critical values for a two-tailed test when I'm doing confidence intervals, right? I'm trying to figure out how many standard deviations to the left and the right do I go to get alpha total in my tails, or half of alpha in each tail. Okay? So I've got half of alpha in each tail, so 0.05 over 2. Sorry, I was thinking ahead. Right, it should be 0.025. Okay. So 0.025 is that area that I want in the tail. I know my degrees of freedom is 50. Right? So I go to that student T table. I say, okay, I want 0.025 in the tail. Degrees of freedom was 50, 2.009. Okay. So 2.009. Now it's just a matter of getting this entered in my calculator. I'll never try to trick you. I'll never give you two that have the same lower bound or the same upper bound. So if I'm looking at these, once I find one of these, I can just calculate the upper or lower bound. Once I identify kind of that, I should be able to get the correct answer. So I won't do something like this, where I give you kind of these two values that are the same. Although in this one, it really doesn't matter, because if I'm looking at this, what does my confidence interval have to be centered around? So if I remember what I'm doing is I'm centering it around whatever this sample difference that I found was. So -1 should be smack dab in the middle of my confidence interval. If I'm looking here, -1 would be a little bit closer to -1.7 than it would be to 0.26. So I actually can rule C out, because -1 isn't smack dab in the middle. Now you might have to, maybe you can't really see that as easy, but like if you took the difference between -1 and -1.76, -1 and 0.26, you'll see that those are different. And that can't be, because it should be smack dab in the middle. Now, a lot of times I'll do something that's a little bit kinder, which is like, I would only give you a range of positive values. Well, if the sample difference you found was -1, you know your confidence interval could be centered around -1. So not only should it be centered, it has to include it, right? If it's centered around it. So sometimes you can kind of use these principles to rule certain answers out. Right? And I try to think of these things a little bit more on the exam than when I'm writing these practice exams, about giving you things you can rule out if you remember these kind of underlying principles behind what we're doing. All right, so I can use just to be a calculator real quick. So I had what? -1 was that sample difference I found. I'll get the lower bound by 2.009 times square root of, what was it, 9/40 plus 16/50. So just using Excel to be my calculator here. So I get about -2.48. So I can identify that correct answer is A here. Okay. Any questions on that before we keep moving? So let's instead go from confidence intervals to now wanting to do some hypothesis testing. Okay. So with hypothesis testing, right, I've actually written out here the null alternative, but I might ask you to identify the null alternative hypothesis on the exam. So here, anytime you've gotten these practice exam problems, make sure you read what it's saying in words and knowing how that matches up with what we have in our null alternative hypothesis. So here, I want to test for whether or not Indiana has a lower BMI than Ohio. So before I look at the one I was given, if I had to identify that, if I want to know, so I've got this difference and I'm thinking about it as Indiana minus Ohio. Sometimes it like helps to write out the example. If I want to know what I want to test for, that's always my alternative hypothesis. If I want to test for whether or not Indiana has lower mean BMI than Ohio, what am I really saying? I want to know, is that difference? Yeah, right. If Indiana is less than Ohio, it would have to be a negative difference. So what I'm saying in words that Indiana has a lower mean BMI than Ohio, what I'm really saying is I want to test for whether or not the difference is negative, right? Less than 0. So I'll assume the exact opposite is true. That would be a null hypothesis. Right? So if I ask you to identify this, I might give you kind of a thing like this where I want to know, is that group 1, is Indiana less than group 2, mean less than Ohio? If that's the case, I'm testing for whether or not that difference is negative, right? Or I have a left tail test. So just in a more general, I think I'll do this now. So there I was saying, if you've got a statement that says like, and it won't necessarily, it'll probably sit like, I'll have this in words, but so I'm just shorthanding here, but like, if you're testing to see, does group 1 have a lower mean? Or if we had a proportion example, does group 1 have a lower proportion, right? Or a proportion or a mean less than group 2? Well, this would always mean that you're wanting to test for, is that difference negative? Right? Just like this is the problem we just had. So here, anytime you've got group 1 being less than group 2, which is what you want to test for, you've got a left tail test. Anytime it's set up as, I want to know whether or not group 1 is greater than group 2. Well, then what I'm wanting to test for is whether or not this difference is what? Yeah, positive or greater than 0. So I've got a right tail test. And then anytime I have this terminology of, is group 1, is their sample mean or is their sample proportion different than group 2? That means I'm always testing to see, is that difference, doesn't equal or not equal to 0, right? Is that difference any value other than 0? That's a scenario where I've got a two-tailed test. So in identifying these null alternative hypotheses, this will be kind of your general rule. You're testing to see, does group 1 have a lower mean or proportion than group 2? Difference is negative, left-tailed test. Group 1 is greater than group 2, you have a positive difference is what you're testing for, right-tailed test. Different than, you're just saying, is that difference anything other than 0? I've got a two-tailed test. Okay. It's kind of a good shorthand kind of way to remember that. Okay. Any questions on this before we keep moving? Kind of go back to the problem. We'll do a little bit of a side there. We're okay with that? So I've got a less than sign of my alternative hypothesis. So what type of tail test do I have? Left tail test, right? If I wanted to find the test statistic, I go to my formula sheet. I look here, okay, I've got sample means and sample variance. Here's my test statistical equation. I won't spend as much time in class on these and writing them out because it's really just a matter of getting the values that you're getting plugged in and getting comfortable using your calculator, working through more of these examples, right? So here, I've got my two sample means, it's what, 28 and 29. I had the sample variances and sample sizes. I've already used those in the confidence interval. It's a matter of getting these values plugged in, right? So if I'm kind of typing this out in Excel as my calculator, I had what? 28 minus 29 was in my numerator. Divided that by the square root of each group's sample variance, divided by that group's sample size. All right, just using Excel to be my calculator after plugging those values in. Now, one thing I'll notice, so I get negative 1.35 as my test statistic. But one thing I'll notice that if I've got this test statistic, do we remember what does the denominator actually represent here? So anytime we're calculating these test statistics, so the number of standard deviations away we are from our assumed true value, which here we're always assuming the difference is 0, so I kind of made that a little bit easier. This should always represent a standard deviation of the statistic that we're looking at, which is the difference in sample means. So anytime we have a test statistic equation for these two population examples, the denominator always is representing a standard deviation. So standard deviations have to be positive, right? Variances and standard deviations are always positive. So whatever the sample difference I find is, this tells me the sign of my test statistic, right? So read it carefully, set this up, and we would automatically see here, oh, well, the sign of my numerator tells me the sign of my test statistic for these two population examples. I found a sample difference of -1. I can rule these two out right away. Test statistic can't be positive, right? And even now, if I'm having an issue, I have a 50-50 chance, as opposed to a 25% chance of guessing. Now from there, we just sort of plug our values in, the test statistic of -1.25. Any questions on that before we keep moving here? Yeah.
So like the terminology you use, like
Mhm.
that says Indiana has a lower BMI than Ohio,
Mhm.
would it ever be like Ohio has a lower BMI than Indiana? Would we,
I
like,
will-
switch it?
It could be in real life. The way I will write the exams, I will always kind of write it out group 1 relative to group 2,
Okay.
just to kind of keep that consistent. But like I said, even if I didn't, the real way to make sure you're thinking about this correct is probably go up here. Remember, okay, it's group 1 minus group 2. I'm told Indiana is group 1. So I would, if it were me, write out what that difference would be. Then it's a lot easier to think about, like, if I want to know is in there, it doesn't matter, right? Because now if I tell you Indiana is less than Ohio, it's a lot easier for me to think about, oh yeah, that's less than 0. If I say, is Ohio greater than Indiana? Oh yeah, I'm still thinking about, is that less than 0? So if you write it out, I think that helps a lot. Does that make sense?
Yeah.
Any other questions? We're keeping moving here. So we've got our test statistic. The next question. So it's going to be asking us about a critical value. I'm going to show you a p-value one, which isn't on this exam, but it'll be a good one to know how to do. So let's say I wanted a critical value for the 95% confidence level. And because you might have gotten 3 wrong, I give you an assumed true test statistic, right? So we're all starting off on the same foot. And this is how I'll write the exams, right? If you get the test statistic wrong, you probably get the p-value wrong, you might get the, So we're kind of giving you new information at each part. So I've got a degrees of freedom of 50. We already had this from our confidence interval. Let's assume true degrees of freedom. I've got a 95% confidence level that I want. So what would my critical value be? Well, if we recall, I've got this left-tailed test, right? So if I have a left-tailed test, what should be true about my critical values? Yeah, right? Left-tailed test, I'm looking at what value gives me, I think it was 95% level, so an alpha of 0.05 in my left tail. Well, if my Z and my T distributions are centered around 0, if I'm looking at the left-hand side, my critical values will always be negative. And it's going to be the value that gives me that desired alpha in my tail. Right? So 0.05 at a degrees of freedom of 50. I go to my T table. Oops, there we go. 0.05 is the area I want in the tail. Degrees of freedom of 50, 1.676. Now that's not my critical value, because remember the T table always is looking at the right side. But if I know the area to the right of positive 1.676 is 0.05, then the area to the left of negative 1.676 should also be 0.05. Right? This is a symmetric distribution around 0. So I know that I can find the correct value, but then I have to remember, oh yeah, this is a left-tailed test. It's that many standard deviations below, but negative, that many standard deviations away, but below, so negative. Any questions on finding that critical value there? So here's my rejection region, right? For a left-tailed test, it's if I see a test statistic more extreme than my critical value. Well, for a left-tailed test, it's area to the left. Right-tailed test, area to the right. Okay? Two-tailed test, remember, so this is a good recap. So for left-tailed test, we just said we have negative critical values. If I had a right-tailed test, my critical value should be positive. If I have a two-tailed test, remember that's where I've actually got a pair of critical values, same number, one's positive, one's negative, and it's what gives me a total of alpha in the tails. So this is why, like a two-tailed test, finding critical values, it's like going back and looking at those t-values for confidence intervals, right? Very similar, we have to divide alpha by 2 now. Okay, so got my rejection region. If my test statistic was negative 1.55, this is why the critical value approach, if you're making rejection decisions with it, it's nice because it's a really nice visual. I plot my critical value, think about the area more extreme than that is my rejection region. So if my test statistic of negative 1.55, not quite in that rejection region, so I failed to reject at that 95% level. Okay. Questions on that? Or keep going here.
So if it's a two-tailed, that's the only time you do alpha divided by 2.
Confidence intervals and two-tailed hypothesis tests are when you divide alpha by 2. Find your critical values or those t-values you need. Yeah, left and right tail tests, all of alpha is in one tail, so you don't divide them. Any other questions? So I want you guys to ask a comment. This is for you guys to do well in the exam. So you're here. If you got questions, make sure you're asking. Okay with this for now? Okay. So we found the rejection decision using the critical value approach. I think that answered question 3. So negative 1.676, and we failed to reject, right? Let's instead say that I wanted to use the p-value approach. And let's see if I can remember this number. Let's say I told you, actually, yeah, give you a better one. So sometimes don't read into these assumed true test statistics. So in this last example, I happened to choose negative 1.55, which was close to negative 1.35, but I might completely change like the sign of giving you an assumed truth. So don't ever read into them, right? I'm choosing them for very different reasons other than they're close to the correct answer, right? I'm choosing them to kind of make sure everyone's starting off on the same foot. So here I might do something like, assume you found the test statistic was 2.043. And I want you to find, oh, actually, I can't do that. Hold on. This is a left tail test. I need to do this. Sorry. Let's say I told you, otherwise this won't be a very interesting example. Let's say I found you, told you it was negative 2 point. Nope. My brain is, hold on. That's the value I want. Negative 2.403. Let's say I give you that as the assumed true test statistic. Okay. So if that's your test statistic, and I then say, okay, what's the p-value and what's the rejection decision at every level, right? So I might break this up into 2 questions. I might ask you first, just find the p-value. What I then sometimes will do on the exam is like, well, if you got the p-value wrong, you're not going to get the rejection decision right. So on the next problem, I might say, assume you found the p-value to be this, right? So here's my assumed true test statistic. My p-value would be the probability I see that something that many standard deviations away or anything more extreme. So for a left-tailed test, that's going to be the area in my left tail, right? So I'm going to look up this value on my t-table at a degrees of freedom of 50. So I'm going to go down here, degrees of freedom of 50. I go through, okay, I can't find negative values, right? Because it's always looking at the right side, but it's symmetric, right? So I can look up my value, and the area to the right of the positive value will be the same as the area to the left of the negative one. So I find 2.403. I go up. 0.01 is the area to the left of it, right? So my p-value is 0.01 there, okay? Any questions on that idea? So if I ask you for a p-value coming from the student t-distribution, I will give you one of those values that shows up in the table, which is why I changed it from that assumed true test statistic of negative 1.55, because if we tried to look that one up, if I can scroll, there we go. Right? Well, now I'm in between two of these and I have to put my p-value in a range. I won't make you do that, right? I'll give you a value that's assumed true value that's in this table. Okay? Any questions on that before we keep moving? So if I have this p-value, and let's assume, I gave you, this is like, we know what it is, but on the exam, I might give you then an assumed true p-value because if you got it wrong, right? I want to make sure everyone's starting on the same foot. But we know that the p-value is 0.01. What levels can I reject at? Well, I only reject if my p-value is less than alpha. Burn this in your memory. You need this for rejection decisions, for two population stuff, but also for linear regression, right? So if you have the p-value being less than alpha, so is it less than 0.1? Yeah, so we can reject at the 10% level. Is it less than 0.05? Yes, so we can reject at the 5% level. This one's a little tricky. I probably wouldn't be this mean on the exam. But is this p-value less than 0.01? It's equal to it, but we don't have an equal sign here, right? We have to be strictly less than, so we would actually say here we fail to reject that 1% significance. I probably won't give you one where it's exactly equal, but just kind of proving that you still could think about it, right? I'd probably give you like an assumed true p-value of 0.02, right? So that it's a little bit clearer kind of thing. But I wanted to make sure I kind of discussed the PI since I know that wasn't a question on that practice exam, but it could be something I asked you to do as well. Any other questions on this before we keep moving? Okay. So, got that one answered. We will do a proportion one so we can get a little bit of taste of the standard normal distribution. So let's say I have this scenario where I've got gun ownership between US and Canada, right? So I've got these two sample proportions, two different groups. I also have their sample sizes, kept it nice and easy. They're the same here, so I'll mix it up. This is bad. And I want the 90% confidence over the difference between US and Canadian gun ownership. So I've got proportions here. I'm writing this with P's. Hopefully that's a good indicator, like it kind of can remind you. When I go to my formula sheet, I'm looking for the equations that have P's in them, right? So I'll give you the notation. I'm trying to make this as easy as possible so we can correctly identify the set of equations we need, which is here's my confidence interval for the different proportions. Here's my test visit. So for the confidence interval, it's just a matter of plugging in our sample proportions, plugging in our sample sizes, and then we have to look up this Z value, right? So I go back here, I'll look at my example, and I'm just going to start plugging in my sample proportions and my sample sizes. And I'll show that to you here in a second. I just want to make sure I get these. Actually, I can remember how to do this. All right, so I had that formula sheet in front of you, or in front of me, sorry. It's just a matter of getting these values for our sample proportion. This is not 0.026. Sorry, this is 0.26. Right, we're just plugging in what I know. So proportion times 1 minus that proportion for the first group, second group's proportion times 1 minus that proportion, divided by each group's sample size. The last thing I needed was this Z value that gave me alpha over 2 on either side of my confidence interval. So once again, very similar to two-tailed tests, I want to know this Z value that gives me alpha total in the tails or alpha over 2 in each tail. Okay. Now, right away, I know that my confidence interval is going to be centered around that sample difference of 0.06 that I found. Okay. So if I go back here, I forgot the confidence level, so we're going to have to go back to the practice exam. So first of all, 0.06, if I look at these, which can I rule? Which of these confidence intervals can I rule out? Is 0.06 even in these confidence intervals? No, they're only negative values. That doesn't make any sense. So read very carefully. I try to very clearly identify like what group 1 is, what group 2 is, right? So US was group 1, Canada was group 2. We're looking at group 1 minus group 2. I can kind of explicitly define that here, right? So we know that we should have 0.06 smack dab in the middle of our confidence interval. We wanted the 90% confidence interval, so alpha would be what there? 90% confidence, 0.1. So you've got, sorry, 0.1/2 or 0.05 that we want in our tail. We want to find the number of standard deviations that would give us 0.05 in the tail. We're dealing with proportions. So the formula sheet reminds us, but also I kind of wrote that out last class. Anytime we see proportions, standard, normal, or Z tables. So there's two ways I can find this Z value that gives me 0.05 in the tail. The first is just using the Z table, right? Looking up, okay, what's closest to 0.05? I'm in between these two values, negative 1.64 and negative 1.65. Use the higher of the two, right? I've already got kind of the positive and negative sign built into my upper bound equation, upper and lower bound equation. And so I just plug in that Z value. That was the last thing I needed to look up. Everything else, I was just plugging in information I was given. The Z value is what I actually need to look up there. Okay. Now, there's another way I could have done this, which I think is easier, but I also understand why it could be a little confusing. How can I use my student t-table to find the Z value that would give me 0.05 in that tail? Well, remember, whatever area I want in the tail, if I go to the very last row, we said these were the standard normal values, right? If we could ever get a degrees of freedom of infinity, which is theoretically like kind of impossible, but if we ever could, we would have a student t distribution that completely merged to become a normal, standard normal. So this last row we can kind of use as a cheat. If I wanted 0.05 in that tail, the last row tells me that if I was looking at a Z table, I should find 1.645. So I can, basically find the exact same value, but I get to be a little more precise, right? That t table goes out to that third decimal. Any questions for that? Okay. So we've got our confidence interval. The next thing we might want to do is some hypothesis testing with these proportion examples. So I'm trying to keep an eye on time here. So before we look at this, let's assume I didn't give this to you. So what if I wanted to do the hypothesis test that gun ownership between is higher in the US than in Canada? And I've defined this difference. Remember, my group 1 minus group 2 was US minus Canada. So this is where writing it out might be helpful. If I'm thinking about the difference being US minus Canada, and I want to know, I think I said, what is it? Higher in the US, right? So I want to know, does group 1, right? Does the US have a proportion that's higher than the proportion of gun ownership in Canada? So really, what am I saying about that difference there? If I want to know whether or not the US is higher, what I'm trying to test for is that difference, yeah, greater than 0. I assume the opposite is true. Now I've got what type of tail test? Yeah, right tail test. Okay. So we'll keep going here. So I've got a right tail test, right? But I also kind of talked through how we could have identified this was the null alternative if we weren't just given this in the problem. Now, if I'm looking at these test statistics, so first of all, we know the sample difference that we found. So 0.32 minus 0.026, that 0.026 was positive, right? So similar kind of idea. If I'm looking at my test statistic equation, the standard deviation, the denominator always represents the standard deviation of that statistic. So this is the standard deviation of the difference in our proportions. So once again, when we have this assumed true difference of 0, the sign of our numerator tells us the sign of the test statistic. So here, I found positive 0.06. I know my test statistic is going to be positive. So if I look at these answers, I can rule out B right away. Now, this is where I'm going to give you these. I'm going to walk through this, like how I would approach taking a test. We've got formulas. Don't get too lost in them, because sometimes you can have a frustrating day. You might be making the same stupid error on the calculator and you're just not getting it. So let's say I'm getting frustrated by this one. I at very least can rule out B. right? From there, which one of these probably, I mean, this is theoretically possible, but which of these is a pretty wild test statistic? 36 standard deviations away would be very low. I mean, we found a difference of 0.06, but I mean, it's not that different from zero. Right? I mean, that would be an insanely high test statistic. So just what we know about these tests doesn't really make sense. If I'm choosing between C and D, if I work through enough problems, which of these would you maybe rule out? So which of these might show up for things not like test statistics, but for critical values? 1.96 shows up a lot, and we're looking at two-tailed tests where we've got like 0.05 test. So 1.96 could be, it just seems a little fishy, right? So if I was just guessing here, I'd probably go with 1.47. Sure enough, if I actually plug all of those values in, right? So I want to find that test statistic. I go here. This is the one where we had to do 2 steps. First, find this kind of weighted average. Now, this one will be a little bit easier because the 2 sample sizes are the same. The weighted average one will just be the middle value from the 2 proportions. But I can plug all my values in and figure that out. So I end up with P bar being what, 0.029, I believe, if I'm running the numbers correct. So then 0.029, plug in P bar, plug in my sample size. It's just a matter of getting the information and getting plugged into the equation and being comfortable using a calculator to calculate these test statistics. Okay. Hopefully these test statistic problems are easier points in the exam. Right. So I'm not going to walk through that just for the sake of time, but once we plug all those values in, we should get that 1.47, which we could almost pick just on process elimination, just thinking about the principles behind what we're doing. Okay. So instead, let's say I give you an assumed true test statistic of 1.67. Okay. So you've got this test statistic, and I ask you to find the p-value and the outcome of the hypothesis. Okay. So 1.67, I'm looking at an alpha of 0.05. What is that p-value and what is the outcome of the test? I could break this up into 2 questions, so I'll kind of approach that like that since I wrote the exam and might know why I might say I might do something like that. So the first one is, let's just find the p-value. Okay. So I've got this new test statistic. I was told to assume that I found it was 1.67. Now, the p-value is the probability I found something as many standard deviations away from what I assume to be true, or even further. Well, remember, we had a right-tailed test, so that would be the area to the right. Right? So this is my p-value. Right away, just to kind of help remind ourselves to not make an easy mistake, what does this have to be less than? Yeah, why? Yeah, the Z distribution is centered around 0. The area to the left and right of 0 is 0.5. I'm definitely going to have a p-value smaller than that. So right away, if I look at my options, I should rule A out right away. Doesn't make any sense. Okay. So from there, I'm going to look up the value of 1.67 in my Z table, right? So I've got 1.67. So 0.9525, right? Well, this is where I can remember, not make an easy mistake. When I look this value up in the table is going to tell me the area to the left, right? So if I just stop there and think that's my p-value, if I had this drawn out and reminded myself right from the get-go, oh wait, it has to be less than 0.5. I'm going to be like, well, I know it can't be 0.9. What am I forgetting to do? Oh yeah, I wanted the area to the right, so I simply need to subtract that from 1, right? So then I get 0.0475. That's my p-value. Any questions on that? So if the next question I'd phrased a little bit differently, and I didn't give you one specific alpha value, but I asked you what levels can you reject the null at? So here, what levels could I reject the null at? I only reject if my p-value is less than alpha. We've got our benchmark alpha values here, 0.0475. I could reject at the 10% significance level. I can reject at the 5% significance level. I can't reject at that 1% significance level. Sometimes the answer will be all levels. Sometimes the answer will be none of them, right? At a really high p-value. Now, here's what I want to highlight, because we're not going to have time to completely work through a two-tailed test. But I do want to point this out, kind of the only difference that we would have. Okay? If this was a two-tailed test, when you're finding the p-value, there's only one additional step, right? So if I had a positive test statistic for a two-tailed test, I could find the area in this tail, but what would I still need to do? Yeah, now evidence that was equally as far away on the other side would now go against the null if my null was that I assumed it was equal to 0, right? So I can find this area in my tail still the exact same way. The only thing left with a two-tailed test is I then need to multiply it by 2. Well, this would be what, 0.0950. Now I've got a higher p-value. You can kind of see here, if I forgot for a two-tailed test to multiply it by 2, notice now my rejection decisions actually change a little bit, right? Yeah, it's still less than 0.1, but if I had forgotten to multiply it by 2, I would have rejected at the 5% level when I shouldn't have. But, I'm never going to like switch back and forth. I'm just saying, like, if, these are 2 different types of problems you could see. Two-tailed test, you need to make sure you remember to multiply the area you find in the tail by 2. That's your final p-value. One-tailed test, it's just only that area in that one tail. Other questions on this before we keep going? Okay. Is there anything else I wanted to mention here? I think we've got, hopefully. Okay, yeah, we can walk through this one. So the last thing we'll kind of try to go through relatively quickly here are these matched pairs examples, right? So this was like, hopefully these ones are a little bit easier because it kind of goes back to just like a one population, right? So we've got some people here, we're looking at the change in unemployment across different counties. We've got what, 81 different counties. We found that, this difference variable, so 2010 minus 2008, the change kind of in these unemployment rates, the average change over that time period was negative 1.2%, right? So we found this difference variable, right? Same counties, but 2 different time periods. We found the difference. We then found the mean of that difference variable, and we found the variance of that difference variable, right? And you can try to use kind of that notation, d bar s squared of that difference variable d, so that once we go to our formula sheets, we can see, oh yeah, here's our matched pair stuff, right? So you can kind of see, like, we don't have a problem on the practice exam, but I could ask you to do a confidence interval. It's really similar to what we did earlier, right? So when we had sample means and we only had sample variances, it was a much more complicated equation. This is just like we have one mean difference. We've got one variance, one sample size to worry about. And we look up that t-value, give us alpha over 2 on each side of the confidence interval the exact same way we were before. The only difference is now, instead of this really complicated degrees of freedom where I had to give you the degrees of freedom, now it simply goes back to sample size minus 1, right? So I really would just be plugging my values in here. So this is what, negative 1.2, I forget what the variance was, and we had 81 counties. The only thing left I would need is what t-value gives me alpha over 2 on either side, all right? Yeah. Yeah, so I'm not going to make you calculate that. I would, if I give you a matched pairs problems, you will have that sample difference is whatever it is here, negative 1.2. Right? And actually, looks like I might have forgotten the negative sign here in the parentheses, right? Negative 1.2%. Okay. I then kind of have, okay, the researchers want to know whether or not the average difference in the unemployment rate after they increased the federal wage was negative, right? So is this mean difference less than 0? That's what I want to test for. That's my alternative hypothesis. I assume the exact opposite is true. I've got a left-tailed test. Okay. Now, I think I'm going to make this a two-tailed test just to kind of make it more interesting. You have this answer key, so that's fine. Let's assume instead, I just want to know, was there a difference, right? So we get a little bit more, we go kind of through a two-tailed test. Well, the first thing is, hopefully this test statistic equation, once again, it becomes a lot more simple. It's just a matter of getting the values plugged in. You were told that mean difference was negative 1.2. I have to look at the variance again, so I forget the number for that. When we were told the variance, 81 was our sample size. It's going to be plugging those values in, getting really comfortable. That should be matched pairs test statistic. Should be an easier question. That's a much more simple equation than the other ones. Now, I know the sign of that test statistic has to be what? Remember, the numerator always tells me what the sign of the test statistic is. The only thing in my numerator was that sample difference of negative 1.2. So right away, I know that it has to be A, C, or D. Once again, if I'm looking at these, which one might I rule out? 30 standard deviations below seems pretty far. I don't think that's going to be my test statistic. I don't remember what this one works out to be if you work it out. I'm guessing it's a low one. I'm guessing it might be A. Thinking the answer key has the value, but that's just going to matter of getting those things plugged in. What I want to do a little bit more on is if we had a two-tailed test, so instead of this one tail, let's say we had a two-tailed test and we want to make our rejection decision, okay? And we have some assumed true test statistic of negative 1.5. So I'm putting this all into one problem. I might separate this up into two. So the first one might just be, what's the critical value, right? What would my critical value be? And I already forgot. Alpha is 0.05, right? If I've got a two-tailed test, we said for left-tailed tests, my critical values are negative. Right-tailed tests, they're positive. Two-tailed tests, I'm going to have a pair of critical values that give me alpha total in the tails or alpha over 2 in each tail, right? So I had this degrees of freedom, which was what? N minus 1. So we had a sample size of 81. So this is going to be a degrees of freedom of 80. The area that I want in the tail, alpha we were told was 0.05, so 0.025. So I want 0.025 in my tail at a degrees of freedom of 80, just a matter of going to that student T table, right? So my critical values here, if I go to my T table, at a degrees of freedom of 80, I got to go up here. I wanted what? 0.025 in the tail. So I'm in this column all the way down to 80, 1.99. So my critical values will be positive and negative 1.99. Often, if I'm asking to identify this critical value for a two-tailed test on the exam, this is the way I would write it. Right? You've got a pair of critical values, one positive, one negative. Right? Does that make sense? Any questions on this? So for a two-tailed test, my rejection region, anything more extreme than either one of my critical values, so I go like into either tail, right? Now I've got this rejection region. If my assumed true test statistic was negative 1.5, then at the 5% significance level, I actually am not in that rejection region, right? I would fail to reject. That making sense? So just to kind of also highlight just a principle here, what if I wanted to make a rejection decision at the 90% level? Without going through all the steps completely, what's going to be true about my critical values if I go from the 95 to the 90% level? So what's going to happen to alpha? It's going to be high, right? 0.1 instead of 0.05. So dividing 0.1 by 2, I'm going to have a larger area I want in the tail. So in order to get a larger area, my critical values are going to have to be a little bit smaller in magnitude. So at these lower levels of confidence, maybe my new critical value passes that test statistic, right? It's a little bit more likely I could reject it at the 90% level than the 95. Questions on that? You know, I'll give you something a little bit helpful, right? Anytime we just want a certain area in the tail, and I'll do a right-tailed test just to kind of simplify this. So it's going to be a little bit different for t-values. Those are always going to be a little bit off, right? But if you want an alpha of 0.1 in the tail, so I'll kind of think about different areas that you want in the tail that we see pop up a lot. I forgot. There's going to be one over here that we have to do separately. Kind of the z or t value that gives that to you. I'll write down the z value, but the t value should at least be within close proximity, right? It's not going to be that far off. So for 0.1, we'll always find about 0.18 or 0.128. 0.05 is always 1.654, 1.96, 2.33, and then this one is 2.58. Now, obviously they vary a little bit, right? Like, so if I'm looking at a t-value, well, the z-value is 1.96. I found 1.99 from this, right? It's going to be a little bit off, but I should never be getting like at the, alpha of 0.05. I should never be finding, I don't know, 2.5 or something like that, right? I kind of have this list of like sort of the ballpark kind of value should be, even if I'm using that student t-distribution. They're going to be a little bit higher when I'm looking at the student t-distribution, or they're at least going to be like within the same ballpark. All right, I ran out of time here. So any questions before I let you guys get out of here if you have? Okay. So I'll put up an announcement on campus, but I will be around all day Tuesday. So if you want to meet, have some last minute kind of study questions on Tuesday, send me an email. I'm kind of like not doing office hours. It's more like office hours by appointment, just so I make sure that I'm not having like a bunch of people show up at once and have a lot of overlap. Or if people have similar questions and I can make sure I have that overlap. So if you do have some last minute questions, feel free to email me. I can respond via email, or you can kind of set something up for Tuesday. Wednesday, I'll actually, you guys have an extra day. So I've got exams 10 to 2 on Wednesday, but after 2 on Wednesday, I could also probably meet from 2 to 5 if you have some availability and have some last minute questions there as well. Okay. Also, did I badger you guys last class about doing the evaluations? I only badgered you one time. I'm getting inundated with emails. You probably are too. If you really don't mind, it helps me out if you go on and do those student evaluations or faculty. I'll be honest with you, I'm actually not going to be at Ball State next year, but I'm going to be somewhere else. And I'm just always trying to be better. Like I love, like, fill out all the rest of it. I love the comment section. Tell me the things you like, tell me things you didn't like, tell me things maybe, any ideas that you kind of have that help me kind of be better kind of moving forward. Just thoughts in general. I really appreciate it. Okay. All right. You guys have a fun, safe weekend. I will see you next Thursday. And I'll get an announcement up on Canvas that kind of reminds you of the exam date.